In PTC Mathcad, you can perform a polynomial regression. In other words, try to fit a polynomial curve of some order over some data set. And I decided, hey, let's try to do that with some baseball data. So I downloaded a whole bunch of hitting data from baseballreference.com and decided, let's take a look at home run data over the years. And so here you can see all the batting data from the beginning of baseball. And I took that data and narrowed it down to a subset. So I've got the year, and then I'm just doing the data from 1900 to now, and I'm just counting the year from 1900 to now. And here we have the number of teams, the number of home runs that were hit in a given year. And just to normalize it a bit, I have divided the number of home runs by the number of teams because, of course, there have been expansions over the years, and just recently, Baseball Reference incorporated data from the Negro Leagues into the data. So, for example, if you take a look from about 1920, the number of teams jumps from 16 to 24, and then it varies throughout the years until 1948, which was essentially the last year of the Negro Leagues. Back in 1947, that's when Jackie Robinson broke the color line. But anyhow, let's scroll up through here. So really, I'm interested in this number, which is the number of years since 1900 when I'm starting to look at the data, and the average number of home runs. So I want to bring that into Mathcad and analyze it. So let's do it. Here I have my worksheet, and I've documented it with a couple images of great home run hitters. Also, I've got my text box with a hyperlink indicating the source of my data. Let's start off by setting the value of the special variable origin. I always like to use origin with a value of 1. If I go to the operators drop-down menu, I can use the special equal sign with 3 lines, which is the global definition, which just makes sure that this variable has this value set throughout the sheet. Even though I'm at the beginning, I always like to do that at the top. And I always like to set it to 1 for a lot of the things that I do. Now that we have that set, let's create a variable. I'll call it BB for baseball, and that will be equal to, then I'll go to the Input Output tab. Let's use the READEXCEL function, and in this dialog box, I will browse to my worksheet. And here is the baseball Excel file. Let's click the Open button. And right now, it is grabbing from the first tab. Let me change to the second tab with much less data. And we will grab columns A through E. I don't want to grab the second line, which is for 2021. It is 2021 as I'm filming this. It is less than a week after the Field of Dreams game. So this number of home runs for the year, this does not include the whole year because the whole season hasn't happened yet. I'm going to start reading in from the third line. And that'll be interesting. It will skew the data because that third line is for 2020, which was the year that the pandemic started, and we did not have a full baseball season, so the number dips down. So you can see that in 2019, there was an average of 225.9 home runs per team, and then last year it was 76.8. So anyhow, this is good. Let's click the Insert button. So now I have my data read in, and let's use a couple variables to extract the columns that we are interested in. So let's create a variable called year, and I'm going to set that equal to the name of the matrix that was created by the READEXCEL function, and then we can use the matrix column operator function. If I go to my vector matrix operators, that is this one over here. The keyboard shortcut is Control, Shift, and C, but let's just click it from in here. And the year is going to be the second column. Actually, let me change it. I don't want to call it year. I want to call it the index because it's not actually the year. And then let's create another one for the number of home runs, and I'll just call that home runs. that will be equal to BB. This time I will use that keyboard shortcut, and that'll be the fifth column from the matrix. And so that's all that I need in here. Hey, let's take a look at what the data is in a scatter plot. So let me scroll down here. Let's find a place where we can put it, maybe right about over here. Then let's go back to the Math tab. I will put in a chart component. And oops, let's scroll up a little bit. Just wanted to wind up on the sheet. So let's click in here and then insert an x-axis expression. And the first x-axis will be the index. Then let's right click again and insert a y-axis expression. This one will be home runs. And then click outside. And here you can see the data that we are getting. Let's make this a little bit wider. I'm going to double click on here in order to edit the data or format the chart. And so let's start off by going to the x-axis, and for the x-axis I'm going to do a custom setup. Let's do a user-defined range of 0 to 125 with 5 divisions. And then let's go to the y-axis and the setup for that one. Let's change that 0 to 250 and with 5 steps. And then let's go to the trace for number 1, and I'm going to turn on the option for symbols. Let's use the circle, and I want to use a very small circle, so I'll change the weight. Let's turn off the line option. So that way it's just sort of showing up as scattered data inside of here. And so for the setup, while I'm here, I might as well change the name of this. Let's call this the actual data. And that's good. So let's hit the X out of here. So there I have my scatter data showing up throughout here. And you can start to see that, you know, we do have some weird stuff. Hey, there is the outlier for the pandemic year. Here is another low number. So you can see this is roughly about 1980 or so. Back in 1981, there was a lockout where there were 713 games that weren't played. As a result, the number of home runs is much lower for that one. The weird thing is, if you go about over here, back in 1994 over to the 1995 year, there was another lockout where even more games were missed, but you don't see a huge dip in the home run production. Anyhow, we have our scatter plot. Now, in order to get a curve, a polynomial curve, fitting through this data, we're going to use a function called polyfit. Let me go to the functions tab, and these different functions for doing what's called a multivariate polynomial regression are actually located under the design of experiments group. And we're going to use polyfit and polyfitc. And the first one we'll use will be polyfit, which will create a function that will go through this data. And so I'll choose order 2. I'll use that as the name of my variable. We're going to have that be equal to, and I'm just going to type in the name of the function manually. And the first argument that you send to this is going to be the x values, which in this case will be index. And then the second one will be the y data, which is home runs. And then we're going to specify the polynomial order of the curve that we want to fit through there. And this one will be 2. And let's repeat that a couple of times for a third order and a fourth order polynomial. Order 3 is going to be equal to polyfit index home runs. And then we'll get a third order polynomial. And let's also do order 4 is equal to polyfit index home runs. This will be a fourth order polynomial. To place these different functions in our scatter plot, I need a range variable, so I'll call it range for lack of originality. And then we'll use the colon equals, and this will go from 0, and then I'll use the keyboard shortcut of hitting 2 periods for the range, and we'll go out to 125, which corresponds to the length of my x-axis in the scatter plot. So now that we have this, let's add in a few more different functions into our plot. And so let's right-click in here, insert another x-axis expression, and this one, the x-axis expression will be range, and then for our second y-axis expression, this will be order 2, the name of this function over here, and then in parentheses, we're going to send to it the range variable that I called range. Let's click outside, and here you can see the second order polynomial that is fitting through the data. Once again, we can double click on the graph, and let's go to the second trace, and maybe I want this to be a brighter color. Let's make it red, so that's good. And let me change the name of this to second order for the polynomial. Let's go to the setup for the chart itself, and it doesn't have a legend. Let's put in a chart legend in the top left, and let's have it with a single column, and so that way you can tell what the data is. Let's hit the X out of here. So there we can see what the second order polynomial looks like fitting through the data. Let's repeat that again. Let's put in our x-axis expression, and this will be range. And then we'll do another y-axis expression. This will be order 3 range. And so you see there it curves a little bit differently as it tries to match the data. Let's do that one more time. Oops, let me use the right mouse button to make sure that I'm getting the correct variable. Let's insert our x-axis expression, and that's going to be range. Let me get in a little more space down over here where I can fit in. There we go. Let's put in our additional trying to find some place I can get another y-axis expression in here. And so this will be order 4 range. I'll rearrange this stuff in a moment and then click out over here. And so there you can see it. Let me see if I can fit everything up a little bit tighter inside of here. And once again, we can update the graph. Let's double click on it, and let's go to our third trace, and let's change the color for this one. Let's make it a bright green, and for the setup, let's call this third order. And then for the fourth trace, let's change the color of that one to the bright purple, and let's go to the setup, and this will be for the fourth order. And that looks good. Let's hit the X out of there. So that way I've updated my graph so you can see the different order polynomials being fit through our scatter data in here. And let's take a look at how we can update the data and the different graphs. We can see how this is moving up, and we can see, depending on which polynomial order that you're using, we can see that we should be able to expect an increase in the average number of home runs by team going into the future for the second and fourth order polynomials, but not the third order polynomial. And it's this data from 2019 that is really skewing things. So let's go up here, and I'm going to change the READEXCEL function, and I'm going to say, hey, let's not get that line for the 2019 data. I'm going to change this to A4, and then when I click outside, let me scroll down before I do that, take a look at how the graph is going to change. So there you see how it updates based on that one data point that was skewing everything off from the pandemic year. All right, so that's good so far. You can see how I'm fitting these higher order polynomials through my data. But what if we wanted to access the coefficients? We can use the polyfitc function in order to do that. And so let's create a variable. I'll call it C2 for my coefficients of the second order. That's going to be equal to polyfitc, and our first argument sent to it will be the index vector, and then our home runs, and then the order of it, second order. And so then we can evaluate this. C2 is equal to, and you can see how the data here automatically shifted my view of my worksheet to the draft view because there's so much information that is reported here that it is going off the side of the page. Let me select this and go to math formatting and change the size to a format of 8. And let's go to the document tab and change back to the page view from the draft view. And let's copy this a couple times. Let me hit Control C and then somewhere else and Control V, and then paste it one more time, Control V, just so that I can save myself some typing. So the coefficients for the third order polynomial, let's change the variable name and change the polynomial order and do that one more time. C4 is equal to polyfitc for those different arguments and the fourth order polynomial. And now let's evaluate the C3 matrix, and let me grab this and drag it down a little bit and evaluate the C4 matrix, and that's equal to that. Hey, let's change these. Go to the math formatting. Again, I like the page view, so I'm just going to make that smaller, and then document, change from draft view to page view. So let's take a look at what these different matrices are for the polynomial regression function that returns the coefficients. So you can see that we have multiple different columns over here. And so the first column is for the term that it uses. And so intercept, that refers to the y-intercept. So for example, if you have a first order polynomial, well, that function is y equals ax plus b. The intercept is the b. It's where the curve intercepts the y-axis. And then we have the a term. So this is the coefficient for the first order variable. And then the a term is the coefficient for the second order polynomial. When we did the polyfitc function for a third order polynomial, here you can see that we have a. And so that means that this last row here in the matrix is for the coefficient for the third order polynomial, and correspondingly, if we go to the fourth order polynomial, we have a. And one thing to note about this is that when you are using this polyfit function, you can actually use it for multiple variables. So you could have a's and b's in there depending on the arguments, like the values that you send into the function, because these don't have to be vectors like I'm using. They can be matrices. But anyhow, let's talk about these other different columns. Here we have the coefficient column. So these are the actual values of the y-intercept and the coefficient for the first order and the coefficient for the second order, and the coefficient for the third order and coefficient for the fourth order. Then we have a column for the standard error for the regression coefficient. And then we have the lower bound and then the upper bound of the confidence intervals. And then this VIF, that stands for the variance inflation factor. And so it means it's the measure of the inflation of the regression coefficient due to multicollinearity. That's a mouthful. Then we have this column for T. So this is the student's t-test statistic to test if the term is significant. And the final column that you have here is P, which is the p-value for statistics. It's the probability of rejecting the term based on the t-statistic when in fact it is significant. So all of you who are really into statistics and testing and quality of fit, that should be familiar to you. But I just want to show you that, let's say that you wanted to use one of these coefficients in math, you can do that with the matrix element operator. So for example, here we have C4. I will type in C4, and then if you go to the matrices tables tab underneath operators, it is this one over here, the third one, the matrix index operator, which is the same thing as the left bracket. I'll click on that. And so if we want to extract the value from, say, the last coefficient here, the fourth order coefficient, that would be 1, 2, 3, 4, 5, 6. So let me type in 6 and then a comma, and it is the second column. And so then when I hit the equal sign, hey, there you can see this is how you can use the different coefficients in additional functions or evaluations that you want to use. So again, that is the basics of using the polyfit and the polyfitc functions for polynomial regression, fitting curves through data. I hope you enjoyed this video. For more information, please visit www.creowindshield.com. If you learned something from this video, please give it a thumbs up. And if you like this video, please click the subscribe button and ring the bell to be informed when new videos are uploaded. Thank you very much.